Thanks, everyone. If anyone has trouble hearing me, let me know. I'll pump up. Okay, thank you. Okay, so thanks everyone for coming. First of all, it's cool that a lot of people are interested in types. So you're my people. So thanks. Okay, so uh, I want us to talk about uh, this paper by Oleg Kiselyov and Chung Chie Shan. I hope I'm saying that right. Uh, that's the URL, and I've put up the slides on GitHub. And sorry, I made a typo, and I in the GitHub URL, and I'm scared to change it now because I don't want to break links. So this thing is not a typo, but the original link is a typo. Okay, so the basic requirement that you need here to use this technique of lightweight static capabilities is a statically typed programming language with parametric polymorphism. I left that out because it's a little big here. But yeah, you do need generics. And you can do slightly more complex things, more type-safe things with a little bit more power in your type system. But still within the realm of programming languages that are in industrial use today, like OCaml, Haskell, Scala, even to an extent, I would say C++. And you'll see something about that later as well. So let's give you some motivation for this. So the basic idea is that we want safety in our code. So, it's great to get as much safety as possible before you ever run your code. And type safety is a great way to do that. But the problem is that as you go further and further into the type spectrum, things get harder and harder to type properly, because essentially what you're doing is you're proving things about your programs, and the proofs get more and more difficult as they get more and more complex, as the things that you're trying to prove get more and more complex. So the authors said that, okay, what if we could kind of mix together static typing and also dynamic typing and try to find a middle ground between them and try to use them together like in a kind of harmony and like a symbiotic relationship. And one of the nice things that you can do if you try to do that is you, instead of doing multiple runtime checks for throughout the life of a program for any particular piece of data, you can do the check once and guarantee that the check has been done by using a static type, and then you can pass around that typed piece of data to everyone who needs it, and then they know they have an assurance because of the type system that the check was done, so they don't need to do it again. And I'll show you what I mean in just a second. So the ideas here are that you have a small piece or kernel of trusted code that you wrote and you verified manually, and that you gave it a unique type with a unique name. You wrapped up that code with that type, and that says that I certify this code, that I checked this, I tested this, and I certify it with this type. And another concept here that you will come across is that you will have proxy types that represent dynamic runtime values. So we're not fully into dependent type territory here. So what we do is we use a bit of a hack, but it's a reasonable hack sometimes. And I'll try to show you guys an example of that as well. So let's start with a simple example first. And this is trying to reverse a list. And this is obviously a trivial example, but just gives you an idea of the concepts in a concrete way. And is this readable? Should I zoom in? It's okay. Okay, so let's do a basic reverse, and this is an OCaml. And so what this is saying is that the rev function REV, is a recursive function, and it takes a list and it takes an accumulator, and it gives you back, if the list is empty, then just the accumulator. Otherwise, it will give you back the recursive call to itself, the result of the call, with the tail of the list and the cons of the head of the list and the accumulator, which is just the standard list reversal, a functional list reversal. So you could ask, why don't we use pattern matching here? That would be the normal statically typed functional way to do this, because with the benefit of using just functions is that you can target any data type which supports those functions. So it doesn't even necessarily have to be a standard linked list data type. So now here's the problem. You have runtime checks in 3 different places for the exact same thing. So you check that the list is empty, first of all, at the if null list. Then you check that it's empty at tail list, and then again at head list, because they have to do those checks because they need to know whether to throw an exception or not at runtime. Because if you don't throw an exception, and if you just allow getting the head of an empty list or tail of an empty list, you're going to allow pointer overruns or security holes. So these languages, they all do these checks and they throw exceptions to be safe. So this is the problem is that the same check was done 3 times, and this is symptomatic of this kind of code. Is that when you don't certify a piece of code and you're not able to reuse that same check over and over again, you end up having to do it multiple times. So let's try to do that certification right now. And one way to do this is with this OCaml data type and its associated functions, and they're all encapsulated inside a module, and I'll just explain what this means. So you have the type, we call this apostrophe A alpha, just OCaml people like to do that. So you have a type alpha t, which is a generic type, and a type t, which takes a type parameter alpha. Like it could be like a list of, as you can see internally, it's a list of alpha, but to the outside world, you can think of the top portion as an export list. This is what's exported to the outside world. And what's exported is that this is an abstract type alpha t, which is a type t, which takes a type parameter alpha. And it has a few functions which convert from an alpha list to an alpha t option, which is saying that if you give me a list of something, I'll give you back t of that same thing, or I'll give you back none if I couldn't do the conversion. And then you can do a conversion back to the lists, which is fully lossless, because if you have an alpha t, you have a guarantee that you have an alpha list. So you can just do that straight away. And then you can take the head and tail of an alpha t because they're guaranteed to be non-empty. Oh, and I didn't mention the name before. The module is any list, which I should have probably called it non-empty list. It's supposed to be a non-empty list. So I'm trying to guarantee here that whatever list alpha t object you get back from here is not going to be an empty list. So now we see the implementation, which is fairly simple as well. We just say that an alpha t is an alpha list internally. We don't have to allocate any new anything new on the heap, and we just directly store the list that was given to us. And the trick here is that when you convert from a list to an alpha t, to a non-empty list, you check if the list is null, that is empty, and then you say that it's empty, so I'm just going to give you back none. And if you check if it's not empty, then okay, it's not empty, so I'm going to give you back some of your alpha t. And the toList and the head and the tail functions, now you can say that toList is just, I already have the list, so I'm just going to give you back the list that I have. And the head and the tail are, we're going to assume that there's an unsafe head and tail which does not check and throw exceptions. And if you really know what you're doing, then you can use these unsafe functions. And we do know in this case because we've already guaranteed that our list is not empty. So we're just going to go ahead and do that. Okay, now with that, let's implement a smart reverse, what I'm going to call a smart reverse. It does the emptiness check only once. So let's do a reverse with the same list and an accumulator. Let's convert from the given list to a non-empty list, and let's check if what we got back. If we got back none, that's nothing. Then we just say, okay, the list was obviously empty, so give you back the accumulator that you gave me. And if the list was not empty, then I got a sum of list, and I'm going to give you back the result of the recursive call to myself with the tail of the list and with the cons of the head of the list of the accumulator. And now the tail and the head calls here are efficient because they don't do those null checks again. So you did a check only once, and this is how you avoided that inefficiency that you had before. But you can point out that you are creating an option value on each iteration, on each recursive call. The paper actually shows you a continuation passing style. So instead of giving you a alpha t option, it would give you it would give you a function. The from list function would give you two slots to put in functions for what to do, basically callbacks, like JavaScript callbacks for what to do if the list was empty and what to do if the list was not empty. And that way you just keep going with callbacks, and you don't need to create any new allocated option values, sum or none or anything like that. Okay, so that's a simple example. Let's talk a little bit about the formal semantics of how this works. And I'm not going to go into type theory, typing judgments, or anything like that. I'm just going to, just give you guys an overview. So how this works is that there's a strict and there's a lax language. And these are two formal languages. And what the authors did was they said that the strict language is a language which is sound, and they formally proved it. And it doesn't allow things like creating a non-empty list that actually contains an empty list. It forbids that. So it formally forbids that. So you just cannot do that in strict. So as you can imagine, strict is not Turing complete because it doesn't allow you to do anything you want to do. So and that's the point, because you want safety. You give up some power and you get back that safety. And what you do next is you convert from strict into a slightly lower level language called lax. And it's kind of like a transpile from some static language into JavaScript. You essentially keep everything that was happening before, it's just that you transpile it into JavaScript. In this case, lax. So lax is a slightly more relaxed language, and it allows you to have incorrect code. But the beauty of it is that you actually won't have incorrect code because formally what you did was you wrote your code in a way that conforms to strict, and now you view it through the lens of the lax language, and suddenly the code is still safe. It's just that the lax language can be embedded into modern statically typed languages. And we saw an embedding just now with the list reverse example. So these things are abstract, so you don't need to you don't need to imagine that these have concrete, actual strict and lax languages. They're more typing rules and judgments and so on. You can check out the paper if you want to see the formal mathematical symbols and all that stuff, which proves that. And so with lax, what you can also do is you can visually inspect it in your target language, like OCaml or Java or C++ or whatever, and you can just visually inspect it and prove that it's correct. So that's where we come to types. We kind of like shift our view of types, and we now think of them as a language, a DSL for expressing static capabilities. Static capabilities are, if you, the paper goes into this a bit more, but you can think of capabilities as permissions which allow you to do things. Like if you have a capability, they're like user roles or logins or authentications. So If you have a capability of administrator, you can log into a system and do whatever you like, right? So types can be thought of in a sense like capabilities. If you have a certain type, you have a guarantee that you can do something. So again, what you do to get types as capabilities is you have a you write again your domain specific operations like we did with our non-empty list. The domain was that we need to make sure that the list is really not empty. So you use an expressive programming language like you know OCaml or Haskell or Scala or something like that. Uh, the lower the expressive power, the less you can express, obviously, but you can still do some things, and I'll show you guys examples later. So now these assertions are wrapped in a kernel of trust, as I mentioned, and they have to be visually inspected. Or you could, with more effort, with more type theory, you could formally verify them. The paper shows examples of this. So now capabilities, as I mentioned, the types certify that certain conditions hold. And what's more important is that they propagate those certifications throughout the rest of your system. So once you have a non-empty list value, that the type of that value certifies, wherever you send it throughout your system, it carries with it that certification that this is really a non-empty list, and you don't need to check again. So now abstract data types, as you guys know, are data types which you have complete control over. You provide only the operations that you want allowed, and that's what really makes them so safe. That's what allows you to embed the strict language inside your daily life programming language. Uh, so, and one of the reasons for this is that they are, like I said, tied to control, and also because their names act as the unique identifiers of those certifications. The very names of the types. And so abstract types are very good models for capabilities. And as I mentioned before, there is also the concept in the paper that you can tag or proxy dynamic value runtime values with static compile time types. For example, if you have the number 0, the number 1, 2, 3, 4, you can't represent them directly in the type system as just numbers, but what you could do is you could represent them as the types, some type Z, which represents the number 0. And then you have the type Z next, perhaps. You can define a static abstract type, which represents the number that comes after 0, which is 1. And then you could have Z next, which is 2, and so on and so forth, going on for all the numbers. So this is kind of what this part means, is that you can convert dynamic values, which you can't otherwise represent at compile time, into static types. In some cases, numbers are probably the most common use case of this. So for example, you can tag an array with a type that says that this array is bounds safe. It doesn't allow, oops, sorry. That's not there. Okay, so this array doesn't allow bounds unsafe operations, or it does, depending on the type that you tagged it with. So for example, normally you have an array of A or an array of element, but you could actually have an array of element, and then you could give it another type parameter that says safe or unsafe. And that type parameter acts as a tag that tells you that this array allows or disallows bound safe or operations.
So the type parameter would be safe, not something like Z next.
Oh yeah, sure. Okay, so it depends on what you're trying to model, right? So if you're trying to model arrays which have bound safe operations, then you'd use some safe or unsafe probably. If you're trying to model something else, let's say for example a type level balanced tree, then you would use that Z, you would use Z next, and so on, to model, for example, the height of each node of the tree. And you would assign it, you would tag it with that type to represent its height in the tree. And then in that way, you would balance the tree.
With the safe version for bound safe operations, is that declaring that the implementation of the array is somehow not going to allow you to ask for a number that is outside of bounds?
What usually you will do is you will provide functions for which only work with the, the array type that's tagged safe, and those functions will, by the very implementation, by the fact that you implemented them in that way, they will only allow safe operations. And you will also provide another set of functions for the arrays which are tagged as unsafe, and they will allow unsafe operations. Again, by the very fact that you allow those operations. Um, and that has another name as well, that technique, which I'm not going to mention here because you guys can, we can talk about that later. I don't want to kind of move off into other territory as well.
That sounds very mysterious.
Yeah, no, I mean it's not. I mean it's just that I want to keep it focused on lightweight static capabilities right now, but we can touch on that later as well. Okay, so there's an example in the paper of this. I didn't include this in the paper because I'm not sure we have enough time. But I prepared some code samples. If you guys want to check out the GitHub, I'll probably want to put a bit more documentation comments in the samples after the talk. Okay, so looking back on some of these techniques. The authors really found that ML language type systems with, Hindley-Miller inference and the kind of higher level, type level tricks that they allow you to do are really a perfect language for this kind of static capabilities. And you can kind of use other languages as well to implement some of these features, for sure. We'll see examples. But again, the ML languages just seem really like a great fit. So if you ever try it out, then you might find that it's just more powerful. Of course, the obvious limitation is that you, the implementer, are kind of in total control of this whole thing. That if you kind of, for whatever reason, you got distracted or whatever, the code might not be as correct as you thought. Obviously, that can happen anytime, but this is really crucial because this is your one place where things go wrong. That's the implementation, and that's the one place where you need to get things right. So obviously, you don't have a formal guarantee unless you put in the hard work of getting that, working out the formal semantics of your code. But again, since you isolate that crucial piece of implementation into a small piece of code as possible, it's easier. It's easier for you to either visually inspect it or even formally verify it. So I would argue that it's still very useful to do this because it's just easier.
When you say that's easier, do you mean, for example, with our reversing example, it's easier to look at that small piece of code that we wrote that does the verification than it is to ensure that you have proper null checks at every call site in your program. Is that the differentiation? Or?
Yes, and sorry, I've been totally lax about this myself. I need to repeat the questions. The question was that is it easier because you just need to do the verification in one place rather than multiple places throughout the call sites? Was the question? And yeah, that's exactly it. It's easier because you're doing the verification in that one, hopefully small piece of code, and the check for the non-emptiness. And throughout the rest of the code base, you don't check at all because you're 100% sure because you have a type level guarantee. So you have a certification. So that's it.
I don't know if this is the right time for this question, but how does that connect to the strict versus lax languages?
Okay.
Are you writing the check in strict and you're calling it in lax, like the call sites are lax?
Okay, so how does this connect to strict versus lax languages, the formal semantics? So I think, from what I understand, what happens is that you write the implementation, the small implementation, as if you were writing in a language called strict, with the semantics of strict, uh, but you kind of do like a identity transformation, and you kind of just look at it in a different kind of way, and at the same time, it becomes a lax language because it's already embedded inside your language that you were already using.
But we don't get the advantages of actually writing it in strict that we would get in terms of our ability to formally verify that.
Exactly. You don't, but you could if you spend the time to do that.
Okay.
I was just wondering. I'm not sure if you're familiar with Rust, but how does Rust's unsafe blocks and like the formal text system of the rest of the language map to this idea?
How do Rust, unsafe blocks, and the rest of the type system map to this idea? Rust, I think you raise a great point because to me it seems that that's a pretty direct and literal implementation of the strict versus lax idea, because the Rust borrow checker is a kind of implements a strict semantics for ownership, but the unsafe part of Rust discards all those checks, and so you can think of that as a lax semantics language. So strict versus lax, that's a very good example of that. Okay, so I think I uh, covered that. So they in the paper they compared this uh, technique, lightweight static capabilities, to dependent types like type systems like you get with Idris or Agda or F-star or those systems. They actually compared with dependent ML, which is a slightly older system, but it's similar. So basically, lightweight static capabilities are formats dependent types. Um, and instead of doing certain powerful things that you would do with dependent type systems, you do less powerful things, but you do them because you get some of the power as well. You still get some of the power. You don't get all of the power. You don't get the power of lifting values straight away to the type level, but you still get the power of lifting or encoding some values as type level proxy types. And again, instead of fully trusting a formally verified piece of code, you you manually verify and trust to a certain extent that you got this implementation right. So again, trade-offs for sure. And I mentioned before continuation passing style. In OCaml, because of OCaml's great tail call elimination, you can use CPS for performance instead of to be able to avoid allocations. But obviously, it's pretty ugly because callbacks are ugly, callback hell. Uh, so you might be able to use a more optimizing compiler. Some compilers do full program optimization like Milton. Some compilers have settings that let you do higher and higher levels of optimization. OCaml has an F lambda thing coming up, which might be able to do it. Uh, so it depends. I mean, what's your tolerance for performance levels, and what's your tolerance for compile times? So again, I wanted to emphasize that this is not just OCaml. So let's look at something that I have an argument about this with this one guy on the programming Reddit every time some article comes up about static types, and he always says, "Can you? But how do you make sure that that a list is sorted statically in your type system?" And I say, "Well, you can use lightweight static capabilities," and he's like, "No, I don't think so. You do, but with closure spec, I can just the spec can verify for me at runtime." So I'm like, okay, so I show this example, and let me explain this example. It's pretty cool. Um, the implementation is that the sorted list of A is a wrapper for a list. It's just a composition, and it takes some A elements which are comparable to each other. They can be ordered, and it stores it internally. And when it stores it, it immediately converts. It immediately sorts it, and when you ask for the list back, it gives you a shallow copy of the list so that you get back the sorted list and you cannot modify the sort order of the original internal list. So that's how we achieve the strict semantics. So again, some implementation notes. This is obviously not a value type. You see that it's a class, so you're going to pay an allocation cost. Because that's just Java. It doesn't have OCaml level type alias abstract types. So that's a price here. And as I mentioned, you immediately have to make sure that you sort your list, because if you forget, then it just misses the whole point of the whole class. And again, I used this comparable constraint to make sure that the list elements can be sorted, because when you call the sort method on a list with null, it requires the elements to be comparable, just Java. And so yeah, shallow copy of the internal list. Again, you could have used an immutable list type from the very beginning, or you could just use the Java list and return the shallow copy, whatever. So some trade-offs is that, again, you have to manually implement the sort, and in return, you get the certification that a sorted list of A is in fact statically verified as a sorted list. So you see the kind of synergy here. You dynamically implemented it, but once you have the sorted list value, you have a static certification that the list is actually sorted. So it's kind of a best of both worlds approach. You get the succinctness of dynamic typing at a little bit of cost, but you also get the sort of verification value of static typing. So now any function in your code that wants a sorted list, you can give it a sorted list of A, and that function will now have a guarantee at the type level that it's sorted. So now that function will not need to sort it again, ever. No function, ever. So again, do it once and reuse it everywhere. So that's a huge payoff. Okay. Yeah.
So, sorry, this is slightly long-winded. I just want to see if I have my understanding right now. I think I had it backwards at the beginning, where I thought that what you were writing as your trusted kernel was formally verified, and then you were writing more dynamic code that was making use of that. But I think it's the opposite. You're writing dynamic code that you manually go in and formally verify with your eyeballs, and then it promotes something to the type level that the rest of your code can then use statically. Is that what's
So the question is that is it true that the kernel implementation of the code is actually the dynamic part of it, that's captured inside a single kernel of code, and the code which uses all of that, all of the code which uses it, gets to use it with static guarantees of that implementation that are indicated by the type itself. Yeah, that's absolutely correct. So the kernel of code is the weak part. It's the soft inner yolk of the egg, but the hard shell of the egg is the type level guarantee that whatever's inside, I certified it, here you go, this is good to go. You use this.
So our trusted kernel is trusted.
Yeah. It's trusted. It's like an egg yolk, right?
Trusted by verified.
With your
Trusted.
eyes.
You trust it, you hope, you pray, and you comment, you document, and you hope the next guy doesn't come along and mess it up. Okay, so there's a bonus round to this game. Just kidding. Just today, I found this example. Somebody posted this on the program Reddit. And this is a C++ library which lets you wrap up your values in various type level tags. So for example, you can say that my wrapped value is not negative, it's a non-negative int, and if it doesn't throw an exception, then now I have a guarantee that it's really not negative. And I can just get it back. Any client code that uses it can get it back, and it can take it as a fact that it's not going to be negative. And again, you have non-nullable types, you have again the sorted list type that I just showed you guys, and this is all in that C++ library, which I literally just found this morning. So yeah, they probably don't know this, or they didn't. They might not have heard about the paper, but this is what they're doing basically with C++. So yeah, it's definitely applicable to a wide range of languages. Some of you might even find a way to do this in JavaScript. I don't know. Remains to be seen. Pretty cool. Pretty cool. So yeah, that was pretty much it.
How would you do it in JavaScript?
How would I do it in JavaScript?
Like what takes the place of the type level to get your static guarantees?
I would probably use a what takes the place of the static type level guarantee. I would probably have to use a closure. Create a function which closes over some values, and it looks opaque from the outside. This is all stuff from JavaScript, the good parts, which I read and forgot a long time ago. But yeah, probably a closure to get some opaque guarantees.
Do you want to tell us the mystery thing?
Oh, the mystery thing. Sure, why not? We can go back over it and look at those proxy types again. The proxy types are, nowadays, most people just call them phantom types. So phantom types are type tags for types that you already had. And suppose that you have a door type. Door can be opened and closed operations. And you want to say, oh, okay, I want some more guarantees from this door. Is it really open? Is it really closed? Who knows? I don't want to close the door if it's already closed. You can imagine if it's an airplane, things might go really bad if you try to open a door that's already open or something. I don't know. So what you do is you tag the door with a type parameter. You call it a door of A, or maybe in Java you would call it a door of A, some type A, and you don't specify the A, but you provide factory methods, static factory methods, to convert between door of open and door of closed. You kind of slot in the open and closed abstract types into the door of A type. So once you slot them in, they become either door of open or door of closed, which at the type level indicates what they are, what their state is. So phantom types are really good for encoding state machines, so state transitions. So you just write functions from one state to the next, and you have a type level guarantee that that state transition happened, and you can't do invalid state transitions. So that's really one of the ingredients that they use here.
But you don't need language level support for the phantom types to be able to use this technique.
You do need probably parametric polymorphism. Do you need language level support? I would say you need some support. Parametric polymorphism is probably the least support that you need. In Go, you probably couldn't do something like this.
What about macros?
What about macros? So macros are they're compile time transformations of your code AST, right? So yeah, I mean, you can probably write macros. You can imagine that you can pretty directly encode the strict semantics in a macro, and then at compile time convert it into lax semantics, right? So that would be a cool idea. Maybe in Clojure. I mean, like Clojure Lisp. Cool, I think that was it.